Alright, we're starting section 5.3 now, which is locating real zeros of polynomials, not complex zeros, just real zeros. And there's some processes that we go through to help us narrow down the possibilities of things to try to find those numbers that are where it crosses the x-axis in a graph. So we're going to talk about the rational zero theorem, Descartes' rule of signs, bounds of real zeros, and their intermediate value theorem. Alright, so the rational zero theorem, you have your polynomial, and again that's just the general formula of a polynomial with integer coefficients. Any rational zeros must be in the form of p divided by q. P is the factor of the constant term a sub 0, and q is factors of the leading term a sub n. So we end up dividing factors of the last term divided by factors of the first term to get all possible zeros, and then we narrow down what the actual zeros are from that. Because if you think of trying to pull numbers from the pool of all real numbers, there's no way you could try. You don't have anywhere to start. And so this gives us, narrows it down considerably on what numbers to choose from. So it doesn't find a single, it usually finds a zero, to be honest. But if they're all complex, it may not find any of the zeros, because all this will do will find real zeros. But it identifies a list of rational numbers that could potentially be zeros. It doesn't say anything about irrational or complex zeros. So that's why sometimes it may not find all the zeros. But it's going to find usually at least some of them. And so that's what we have, why we use and rely on many times the rational zero theorem. So it says for each of these polynomials, list all of the potential rational zeros, then write the polynomial in factored form and identify the actual zeros. Okay, so first we're going to start with A. Okay, and so the factors of A0, so let's just go back because you know where this comes from. If we look here, A0, if you remember, is the n term. So A sub 0 in this one is equal to -3, and A sub n is going to equal to 2. And factors of this, well, the only way to get 3 is 3 times 1. In this case, one of them would be negative. And the only way to get 2 is 2 times 1. So 1 and 3 and 1 and 2 are the factors. G is a little different because A sub 0 here is going to equal -4, and A sub n for this one is 27. Well, there's lots of factors for those, so we'll get to those later. But that's where those numbers are coming from when you see them. It's the last number is A0, okay, and the first number, not the x, just the number, is your AN. A sub n. Okay, so next slide. So we have A sub 0 is 3, so it's plus or minus 1 or 3, and factors of n, which in this case is A3, because n is the highest exponent that you see in your polynomial, is plus or minus 1 and 2. And we take the positive and the negative factors into consideration. And so then we're going to look at P over Q. So it's going to be 1 over 1, 1 over 2, so that's 1 and 1/2. We take the 1 of A0, then we have 3 over 1 and 3 over 2, which is 3 and 3/2. And so if there are any rational zeros, they will come from this set of 8 numbers, positive 1, 3, 1/2, and 3/2, and -3, 1/2, and 3/2. So we're going to do synthetic division, and unfortunately this becomes trial and error at this point to find the potential rational zeros. So remember, with synthetic division, we list the coefficients. We're going to start with positive ones. Start with the easiest ones by all means. Do not start with the hardest ones. Start with the easiest ones there. Okay, so bring down our 2, multiply by 1. That adds to be 7. Bring up the 7. Difference there is 3. Multiplies to be 3, and we have found a 0 because when our remainder is 0, we found a 0. So we know that x minus 1 is a factor. If 1 is a 0, x minus 1 is one of our factors. There's at most 3 zeros because x cubed, however many your degree is, that's how many potential zeros you have. So we can factor x minus 1 times whatever's left, the 2x squared plus 7x plus 3. Once you get to an x squared term, you can usually factor. You continue with synthetic division if you want to, but we can usually factor it at that point. And let me just go through how to factor that again, because some people forget factoring. And so I'm going to go here. Remember, this is A, B, and C. We multiply A times C, which in this case is 2 times 3, and we get 6. And B is 7. So we want two numbers that when they're both positive, because this sign is positive, both my numbers are positive. I want two numbers that will multiply to be 6 and add to be 7. Well, that's easy because 6 times 1 is 6. 6 plus 1 is 7. So we're going to split the middle term. Now that I've found my numbers, I'm going to erase this and write underneath. So I'm going to write 2x squared plus 6x plus x plus 3. So instead of 7x, I've written it as 6x plus x. That's what I call splitting the middle term. Group, put parentheses around the first group and the second group. The greatest common factor in the first group is 2x. That's going to leave me with x plus 3. There's nothing I can factor out of that group, so I want to go ahead and put a plus 1 there. And I still have x plus 3. Now, one of my factors are the numbers in front. So one factor is 2x plus 1. And the other one is the parentheses, but it just comes down as one time. So if you factor out an x plus 3 from this line here, you would end up with x plus 3 outside and 2x plus 1 in parentheses. But it's easier just to kind of stop there and pick one is what's in parentheses, one factor is what's in parentheses, the other factor is made up of what's in front of the parentheses. Okay, so that's going to factor as 2x plus 1 times x plus 3. That's how they get that when I erase this and show it as we go on the slide. Okay, so as we go forward with the slide, we can see that they got those as factors, which means our zeros are positive 1, negative 1/2, and negative 3. We set each factor equal to 0 and solve it for those zeros. And so that will be our answer for A. Now let's go to B. We've got factors of 4. 4 times 1 and 2 times 2. We've got factors of 27. 1 times 27 and 9 times 3. Alright, then we're going to start listing them. And I usually just start with a 1. This is our numerator. Okay, so this is going to be our numerator and this will be our denominator. Alright, and that's called P over Q. So I'm going to start with a 1 right here and then put it over everything. So I've got 1/3. I've got 1 over 1 is 1. Then I've got 1/3, 1/9, and 1/27. Then I'm going to start with the 2. Okay, or then I'm going to go over and instead of the 1, I'm going to use the 2. And if I get into anything I've already got, I don't list it again. So I've got 2 over 1 this time, 2/3, 2/9, and 2/27. Okay, so I'm getting significantly more numbers to work from here. Now the next one I'm going to do the 4. So I've got 4 over 1, which is 4, then 4/3, then 4/9, and 4/27. So there's a lot of numbers to choose from with this particular ratio of factors. And so we'll get rid of my writing and they'll list it nice and neatly printed for you down here. So you can list, they list the whole numbers first, and they list the fractions from, in this case, the lowest denominator and the lowest numerator, then they go to the next denominator and the next denominator. That's the possible rational zeros. So again, we're going to have to use synthetic division. But if you look back, there's 12 numbers, which is 24 potential rational zeros, because we have all the positives and all the negatives of those. But you have to appreciate the fact that even though that's 24 numbers, they're not going to all be part of them. And we also have to remember that's a lot less than if we had an infinite number of numbers to pick from. So at least we've narrowed it down some. So let's think of what we might want to do for choosing our zeros. So start with your integer values. Again, do the easy ones first. So do your positive and negative integers, then work from fractions. Because as you get down, remember, as you find one and it gets simpler, you're going to eventually be able to probably factor. And then if you end up with fractions, it's not so bad. So begin with the smallest values first. So we're going to always usually start with 1 or negative 1. So here we're going to start. We have 27, I think it was x to the 4th, minus 9x cubed, minus 33x squared, minus x, minus 4. And so if this works, we'll be down to our x cubed equation. But first we have to see if it works. So bring down the 27, multiply by the negative 1. Then we're going to add and get negative 36. Multiply and get positive 36, and so that'll add to be positive 3. And then multiply to be negative 3, which is going to be negative 4 when I add it. And multiply and get positive 4, and that's a 0. So we found a 0. So one of our factors is going to be x plus 1. Remember, when that goes to be a factor, it's x plus 1. And so what I know now is I've got 27 x cubed minus 36x squared plus 3x minus 4, and the one factor is x plus 1. Now you can have multiplicities. We could try negative 1 again, or we could turn around and try positive 1, because either one of those, negative 1 could be a factor again, or positive 1 could be a factor. But we're going to start, I'm going to erase what I've got here, and then we're going to start with our next set of trial and error, our next value. Okay, so it's cubic. We really can't factor a cubic very well. So we're going, like I said, we're going to go try another 0. So we'll try negative 1 again, because again, it can be we can have multiplicities. It can appear more than one time as a factor. So we're going to try get negative 27. That adds to be negative 63, positive 63, 66. Well, obviously negative 1 doesn't work again. So it never will work again. Once you've tried it a second time and it doesn't work, you can toss that one out. Don't bother to try it again. So let's try 1. Well, they're going to try 4/3. They must know something I don't know. I would have tried 1 next just randomly, because that was the next easiest one to do. So let's go. Bring down our 27. Now when I multiply 27 times 4/3, to multiply fractions, if I multiply 27 times 4/3, I can look at canceling this. The 3 will go into 27 9 times. So 9 times 4 is 36. So we're going to get 36 when I multiply 27 times 4/3. That will add to be 0. 0 times anything is 0. So then we have 3. And we multiply 3 times 4/3, and that's going to be positive 4. And so 4/3 is another factor. So now we know 2 factors. We know we have x plus 1 and x minus 4/3. And we have 27x squared plus 3. That's a constant. So we know that much. Now we're down to a quadratic, and chances are we're not going to be able to, we'll talk about that in a minute, but we're going to go with this. So let's look. So we have another 0. Now 27x squared plus 3 is not going to give us a rational number as an answer. So the way you would solve that is look at it like this. I'm going to go back up without that and just leave it there. So let's go and look at the 20. We're going to set the 27x squared plus 3 equal to 0 and solve it. And so when we subtract 3, we have 27x squared is equal to negative 3. Okay, and so x squared will be negative 3 over 27. Okay, then we're going to have to square root that. Excuse me. So we're going to have x squared is going to equal to plus or minus the square root of negative 3 over 27. Okay. Now, remember, when we square root a negative number, we're going to reduce that. So that's going to be negative 1 times 1/9. Okay. Now, the square root of 9 is 3. So that's going to be plus or minus 1/3 is how you square root 1/9. And the negative 1 comes out as our I. So it's plus or minus 1/3 I. So our two factors then are the x minus, they're going to be x minus 1/3 I and x plus 1/3 I. Okay? So let's take my marks away. But that's how that goes. You work through that and get that. And so there are factors. Okay. Now, the 27... So I'm going to back up here a little bit to this. I would rather write this instead of the way they wrote it. I would rather go back and remember what I just had when we have the x plus 1. I think this will make a little more sense. I hope it does. X minus 4/3. And when I solve the 27x squared, I'm going to go through that quickly because I already did it once. Plus 3 equals 0. We end up with 27x squared is equal to negative 3. And x squared is equal to plus, the square root then is going to equal to negative 1/9. 3 divided by 27. So x will be plus or minus 1/3 I, which can be plus or minus I over 3. Okay, so my two factors then that I have left are x minus I over 3 and x, plus I over 3. We usually don't want fractions in factors. So let's think about how could we make that not a fraction. So we're going to go back and look at the x minus 4/3. I'm going to write my final answer down here. G of x. We know x plus 1 is going to be it's nice even looking fraction. Let's work next on the x minus 4/3. We can set that equal to 0 for our solution. When I bring that over, I could say x equals 4/3. And then if I multiply both sides by 3, you end up with 3x equals 4. And if I move that back over as a factor, 3x minus 4 equals 0. And so I can change that x minus 4/3 to 3x minus 4. And that would still solve out to be positive 4/3 when I solved it as a factor. Same with the x minus I over 3. We could make that x equals I over 3 multiplied by 3 on both sides. And so that's going to be 3x minus I equals 0. So this can be written as 3x minus I, and the other one would turn out to be 3x plus I. And those would solve out as plus or minus I over 3 when I solved it out as a factor. So I still get the same answer, but that way I don't have the factors are not fractions, which we usually tend to want to avoid. And so that's how that would look when you got rid of those fractions. So I'm going to take away this and go back to what they had. They end up with the same answers. They multiply through by 27, and I think that's kind of confusing. So I tried to explain it a different way. And your actual zeros are -1, 4/3, and we have two complex zeros, 1/3 I and -1/3 I. So really there were only two zeros, real zeros, and those are the only ones that are on the list. Again, the rational zero theorem doesn't take into account those complex zeros. Okay, now Descartes' rule of signs, you have a polynomial with real coefficients. Every time there's a sign change from either positive to negative or negative to positive in the polynomial, you count the number of sign changes, and the number of positive real zeros of f is either the number of variations in the sign or less than this number by a positive even integer. And the reason it's a positive even integer is that whenever you have a complex zero that takes some of your rational zeros, is there instead of rational zeros, they're always in pairs, because there's always a complex number and its conjugate as its pair if there's a complex zero. So say we did our Descartes rule and we found there were 4 positive real zeros. It would be 4 or 2 or no positive real zeros, because we could have 4 real zeros, or we could have 2 real zeros and 2 complex zeros, or we could have all 4 zeros be complex. And then the number of negative real zeros, you substitute x with f of negative x, and then count sign changes, and it's that number or less by a positive even integer. So let's go through and do some examples, or an example or two. So we've got a degree of 3. Both of these have a degree of 3. So at most, they're going to have 3 real zeros. Okay, so let's look at A. We can see that we have a positive 2, a positive 3, and then there it goes from a positive 3 to a negative 14. There's a 1, and then we're still negative. So there's 1 sign change for that one. So that means there's possibly 1 negative real zero. Or 1 positive real zero, I'm sorry. Then we're going to do f of negative x. Okay, plug in negative x for all the x's. And negative x times negative x times negative x is going to give you negative 2x cubed. Then it'll still be positive 3x squared, positive 14x, and minus 21. So there, and I'm going to go ahead and put on my pencil here so I can write it. Here we have 1 sign change. After we multiply this out, all our x's, you see, we look here from negative to positive is a sign change. Positive to positive here is not, and then positive to negative is a sign change. So we have two sign changes. This is for the positive real zero, and this is for the negative. So what that means for us is, by Descartes' rule of sign, there is one positive real zero and either two or zero negative real zeros. So if there's one positive and two negative, we've found all the real zeros. The other alternative is that there's one positive and two complex instead of negative real zeros. All right, looking at this next one, when we look here, we go from positive 3 to negative 10. There's one sign change. Negative to positive, positive to negative. There's three sign changes. So there's potentially all three of our zeros are positive. Or there could be one positive and two complex. 3 minus, remember, less than even integer, so 3 minus 2 would be 1. So there's either three real zeros, three positive zeros, or there's one positive and two complex, according to this. Okay, so let's do the f of negative x. Okay, that's going to end up with negative 3x squared minus 10x, negative 3x cubed minus 10x squared minus 51 fourths x, and then minus 13 fourths. There are no sign changes. Everything in there is negative, so there are no negative real zeros. So when we get our rational zeros theorem, when we have plus or minus this list of zeros, we don't have to even try the negatives because we know there's not any negative real zeros. So that helps us narrow it down, what we can try and what we should try. Okay? There's either three or one positive real zeros and no negative real zeros for this particular example, g of x. Okay. Let f of x be a polynomial with real coefficients, a positive leading coefficient, and a degree bigger than 1. A is a negative number and b is a positive number. There's no real zero of f is larger than b. We say b is an upper bound. If the last row in the synthetic division of f of x by x minus b contains no negative numbers. That is, b is an upper bound of the zeros if the quotient and remainder have no negative coefficients when b is divided by x minus b. Okay? No real zero of f is smaller than a, or we say that a is a lower bound if the last row in the synthetic division when we divide by a has entries that alternate in sign. 0 can count as either positive or negative. So if they alternate in sign, positive, negative, then it's a lower bound. If they're all positive, it's an upper bound. Okay, so it says use synthetic division to identify upper and lower bounds of the real zeros of this polynomial. It's a cubic polynomial, so there's three zeros. We can look at the potential zeros. Okay, so we can test any number as a positive, as a potential upper bound, and then we can test any number. So they're testing 2. So if I put 2 there and make the division, we see that we have a negative number. We don't alternate signs, and they're not all positive. So 2 is not an upper bound. The last row has a negative number. If those had all been positive, we could have said 2 is an upper bound of this polynomial, and that all my zeros would be something 2 or less. So we can begin with a small value and progress to larger ones, and that'll find the smallest upper bound. So we're going to try 3. 3 times 2 is 6, then 9. 9 times 3 is 27, 13. 13 times 3 is 39. All these are positive. So 3 is an upper bound. So that means none of our zeros are going to be bigger than 3. Okay? Every zero is less than 3. So if we had some big numbers in that list of numbers, we could just not even try them. Now we're going to test for a lower bound. We're going to try negative 3. So that narrows it down. All our zeros might hopefully be between negative 3 and 3. So bring down our 2. 2 times negative 3 is negative 6. Add to get negative 3. Then we multiply to get 9. Then we have a negative 5 and a positive 15. Now, they didn't bother to do that because, remember, for the lower bound, we alternate signs. So when we went from 2 to negative 3, that was good. But since we didn't go back positive at negative 5, we know we don't have a lower bound. That's not a lower bound. Okay? So once we know we don't get the alternating signs, we can stop. So we're going to test an even lower number, negative 4. So we go to negative 8, then that's negative 5. Then with positive 20. That'll be a positive 6. So we've got a positive, then a negative, then a positive. 6 times 24 is negative 24. That gives me a negative. So you can see we've alternated signs. So all my zeros are going to be between negative 4 and positive 3. Okay? So for the upper bound, all the last row is positive. For the lower bound, they alternate signs. So all of our zeros lie in the interval between negative 4 and 3. All real zeros. Okay. So now we're going to use the rational zeros theorem. We want factors of 21 divided by factors of 2. And that lists all of our potential zeros, remember? So 1 over 1, 1/2, 3 over 1, 3/2, 7 over 1, 7/2, and 21 over 1, and 21/2, and all of the negatives, positive and negative of those. Now there's a lot we can eliminate because we know our upper bound is 3, so there's no use checking 7 and 21, or even 7/2 because that's 3.5, or 21/2. And there's no use going below negative 4. So when we take those numbers out, we significantly reduce our list. And they didn't put plus or minus in front. They listed all of the zeros, either positive or negative, inside this set notation here. So 1, negative 1, 3 or negative 3, 1/2, negative 1/2, 3/2, negative 3/2, and negative 7/2. Again, the positive 7/2 was too big, so we don't even have to try it. So now we're going to do process of elimination, synthetic division. And I'm sure they're doing negative 3/2 because they know something. Again, I would start with 1 or negative 1 usually just because that's the easiest. So 2, multiply that, 3/2 by 2, and you're going to get negative 3. That'll add to be 0. Anything times 0 is 0. That'll give you negative 14. Multiply that by negative 3/2, and you'll have positive 21, which is going to be 0. Okay, so now we have found one factor, which is x plus 3/2. And we started with a cube function, so now we're down to 2x squared minus 14. Okay, and then we can find those roots using the square root method. So we had, let's go back, we had x plus 3/2. So we have one root is x plus 3/2. And then we'll go over here, if we say 2x squared minus 14 equals 0, 2x squared equals 14. Divide by 2, x squared is equal to 7. So x is going to be plus or minus the square root of 7. So we also have x minus the square root of 7 and x plus the square root of 7. And if we want to write the 3/2, again, you can figure out if we have x plus 3/2 equals 0, x is equal to, we can multiply everything by 2 here, and that'll be x, there we go. that'll be 2x plus 3 equals 0. So we could rewrite that instead of x plus 3 halves, we could write it as 2x plus 3, and then x minus square root of 7, and x plus square root of 7. And that would be our three factors. Okay, so let's take this off and look at theirs. Okay, they didn't write it as factors, they just listed the zeros, which is negative 3 halves, positive square root of 7, and negative square root of 7. For the upper and lower bounds, don't use those boundaries as zeros. That's the caution here. There's always that caution box of something. It's tempting to say, okay, well, if negative 4 is the lower bound, negative 4 must be a 0. Or if 3 is an upper bound, 3 must be a 0. That just tells you that none of the zeros are above that. That doesn't mean that they are zeros. So be careful about that. But it does help you narrow down the list quite a bit when you apply the upper and lower bounds theorem. The intermediate value theorem, if we have a polynomial with real coefficients, if f of a and f of b differ in sign, then there will be a 0 between them. What that means, practically speaking, is if you've got some polynomial, and if you put, say, x is 3, or negative 3, and I get a negative here for the y, if I put it in the polynomial and get a negative value, then it's there. Well, say I put in a negative 1, and I get a positive value. Well, somewhere between negative 3 and negative 1, it had to cross the x-axis. So somewhere between those two numbers, there will be a 0. And that's what that intermediate value theorem, it says there's some value between two numbers where we cross the x-axis. If one of them, when we put it in the polynomial, we get a negative, and the other one we get a positive, or vice versa. So that's what the intermediate value theorem is telling you. And it only tells you that it lies between. We don't know if it's halfway between. We don't know we don't know where it is exactly. We don't know if there's not one between the values. If they don't differ in sign, there's not a 0 there. If they both turned out negative, there's no 0 between them. It's only if one turns out negative and one turns out positive that we know that there's a 0 between A and B. So, show that x cubed plus 3x minus 7 has a 0 between 1 and 2. Find an approximation of the 0 to the nearest tenth. Alright, well, first of all, the way you're going to see if it is 1 between 1 and 2, I'm going to first do f of 1, and that's going to be 1 cubed plus 3 times 1 minus 7, or 1 plus 3 minus 7, or 4 minus 7, which is negative 3. So it's negative. So if I was graphing at x equals 1, y is negative 3, right here, okay? Now, at 2, f of 2, I have 2 cubed plus 3 times 2 minus 7, and that's going to be 8 plus 6 minus 7, 14 minus 7, which is 7. So at 2, I'm up here at 1, 2, 3, 4, 5, 6, 7. I'm way up here. Okay. So yes, somewhere between 1 and 2, there is a 0 because it's got to cross the x-axis to go from point 1 to point 2. Okay. So we did F1 and F2. Found that one was positive and one was negative. Okay, they differ in sign, so there's a 0 between them. To estimate this 0 to the nearest tenth, we can put in more values and shrink the interval where the 0 could potentially be. Put in 1.5 and we'll get 0.8. Okay, positive, but it's smaller. So we want it to be a little smaller to go towards the negative. 1.4, we get negative 0.056. If we put in 1.45, because we went to negative with 1.4, we get 0.398. So it's closer to 1.4 than it is to 1.45, but it's somewhere between 1.4 and 1.45. Okay. And to the nearest tenths, and that was like negative 0.05, 1.4 is pretty close. Okay, that's the end of 5.3. Hopefully we're making some progress on finding zeros of polynomials. If you have any questions, please let me know or put something on the discussion board under this section.